Hello everyone. So again, welcome back to our last lecture session, I guess, right? So today we are going to look at, I guess, a couple of what do we say, examples where anyway, at least I would try to help visualize, or help you try to take a holistic view of what it is we have been up to throughout the class, right? So first we are going to look at one example with respect to VMinTech, right? So before we go further though, keep in mind the relevant process as in, what is it now? The acid base, what else? Complex formation, precipitation, dissolution and redox process, they go hand in hand, and they are never or rarely are they independent of each other in most of the systems, right? So here we are going to consider one particular example first before we dig into such a holistic view, right? So first example that I would like to look at, let's say, is I am going to look at the redox couple of Fe2 plus and Fe3 plus, let's say, yes, and also let's say Cl minus and OCl minus, let's say, right? So here let's say we are going to look at concentrations of total Fe, right, of around 10 power minus 4 molar, let's say, and total Cl, which includes OCl minus, to be around, let's say, 5 into 10 power minus 4 molar, right? So here again, before we look at that holistic example, I would like to, what do we say, portray, let's say, or help bring out the reason for such examples, right? And for that I am going to look at one particular what do we say, scenario where we have two redox couples, right? So earlier until now we have looked at, I guess, calculation of P values for a particular redox couple, but here we are going to look at obviously two redox couples, and obviously if you have a system out there where you have a redox process going through, you will obviously have two redox couples because you obviously need electron acceptor and donor, and they are never, what do we say, independent of each other, right? And the reason being, you will never have a pool of electrons unlike the H plus or H3O plus, let's say, right? That you can have in the water, yes. So here we are going to plug in the relevant values and look at the system, and so we are going to understand the system in terms of the log C pH diagrams, right? So obviously VMinTech will help cut down on the time, and here as you see, I guess we are going to look at total concentration here, as in I can obviously independently plug in the values for Fe2 plus total and Fe3 plus total, right, and Cl minus total and OCl minus total, right, independently now, right, such that the sum of these two is 10 power minus 4 and the sum of these two is 5 into 10 power minus 4, right. But here, because we are looking at what do we say, couple, right, and it is not log C P diagram, pardon me, we are going to look at log C P diagrams. So we are going to try to draw the log C or P and P diagram. How is the concentration of the how are the concentrations of the various couples going to change with the P values now, right? So let's say we are going to choose a particular pH of 7 and try to analyze the system at that particular pH, right? So again, the reason why we don't need to, I guess, give the breakdown with respect to the concentrations of the redox couples is that when it obviously calculates Pe, right, you know, you are going to have Pe is equal to Pe naught minus 1 by n, what is it now, log of the reduced form, right, by the oxidized form, I believe, yes. So anyway, even if you give the relevant what do we say, independent concentrations or individual concentrations for a particular P, though, you will only have one particular ratio of your particular reduced to oxidized forms. So it does not make much difference or any sense rather to at least initially give the Fe2 plus and Fe3 plus concentrations independently and so on. You can, but you know, as you see from here, for a given P value, you will always have a particular ratio of that particular oxidized or reduced to the oxidized forms, and thus it does not really need to be taken into account here, right. So again, these are what I am going to plug in, as in 10 power minus 4 for let us say Fe2 plus, 5 into 10 power minus 4 for Cl minus, and let us try to understand the system, I guess. So obviously for that I am going to move on to VMinTech, right. So let us say here I am going to say pH, I am going to analyze it at 7, okay, and then let us say I am going to have the Fe2 plus Fe3 plus couple mentioned in terms of only the Fe2 plus here, and we just discussed why, right. So here I am going to say it is 10 to the power of minus 4, okay, E minus 4 add to the list, and let's say instead of Cl minus and OCl minus, I am going to just specify that as Cl minus and let the system do its own work. I think we were looking at example of 5 into E minus 4, right? Okay, add to the list, and obviously now I need to be able to specify the redox couples. And now this option where I say, let's say, limit it to those species will not work. Why is that? Because I haven't mentioned Fe2 plus N3 plus and Cl minus and OCl minus. I thus need to look at the relevant couples, so I know they are going to be Fe2 plus N3 plus. I need to add that to the system, right? And again also the Cl minus and OCl minus, wherever that is, right? OCl minus and Cl minus, and I am going to add that to the system too, right? So again back to main menu, I will also say there is a possible solid species, right? And let's say that's ferrihydrite, add, right? And back to main menu, and now obviously you want to be able to get the graph between, right, log C and PE, right? I want to get a snapshot of what the system looks like at different P values, but at a fixed pH though, right? So for that obviously you can do the manual calculations and such, but again that's obviously time consuming, right? And if by now we have the relevant background or understanding of the fundamentals about how to do that, but obviously we are going to skip that now and look at it with respect to vMinTech. So the aspect that we are trying to get at is log C versus PE, right? So from here, let's say I can understand, let's say at which PE, let's say would it be relatively more oxidized form of Cl minus, as in when would OCl minus predominate or such, right? I want to be able to answer such questions, let's say, or try to understand the system now, right? And for that obviously vMinTech has this particular option, as we are aware of, or the sweep option, I guess, right, where one parameter is varied, and here I am going to vary the PE, I guess, right? So let's say I am going to go from minus 10 to I guess 30 PE, let's say, right? So 4 per each, 420 is 80 and 1 81. So I am going to have, say, number of problems is 81, start value is minus 10, right? Increment between values is, what do we say, 0.5, okay, till 30, so it's 2 times, okay, right, that's still 81, okay. And now I guess I am going to have to say what do we say species am I going to look for. So obviously Fe2 plus and log concentration. And why do we choose log concentrations? Obviously because the values are going to be relatively less. So if I take the logarithmic value, it makes it for easier understanding of the system, I guess, right? So I am going to have Fe2 plus and Fe3 plus, right? And also obviously Cl minus and OCl minus. And what else, let's say, and now let's say I am going to, instead of all these are possible species, but let's not try to list all these species, but let's look at some of the complexes that I know we usually form, I guess, right? So let's say with respect to this particular complex and FeOH thrice negative, that's with respect to Fe2 plus, I am not going to go there, so I am going to have this. Or let me just add the complexes, I guess, let's see for the either Fe2 plus or 3 plus, and I think a few were repetitive, so let's go back and do that. I am going to just add the various complexes and then try to understand the system. Right, and let's say hopefully we have covered most of the usually formed complexes in it, right? Okay, so let me have a look here. Okay, I still have a couple of complexes out here that I guess we haven't included. Okay, so now we are going to run the system, right, and then obviously export these to Excel and then understand, let's say, which species are predominant at which particular P, obviously at a particular pH value, right? So obviously I am going to have to say save and back, and hopefully everything is in order, right? And then okay, and this E minus 4, okay, that's because of the redox couple that we have specified, I guess, that's fine. pH is 7, so I am going to run MinTech, let's see, and I am going to look at selected sweep results. Okay, so from P of minus 10 to 30, which is what we were looking for, right? But obviously, looking at the tabular information in form of a table, it's difficult to understand what's happening out there. So we obviously need to, so printing the data to Excel, right? And here we have the relevant, what do we say, columns here, PE and the various, what do we say, species. So for ease of, what do we say, or for efficient time management, I already have the graph here. So let's try to understand this particular data here, right? So here keep in mind that the pH is fixed, it's at 7, right? And then here we have on the y-axis log C, right? Logarithm of various concentrations of various, what do we say, the two redox couples, and the complexes based on what our background is, I guess, right? Some of the complexes, not all the complexes though, right? Because if we had all the complexes, the, what do we say, the graph would have been too garbled, I guess, right? And would have been difficult to understand or such, right? So here let's try to understand the system. So here you have PE here, PE on the x-axis and log C on the y-axis. So first let's try to understand the system with respect to Cl minus and OCl minus, right? So obviously as expected here, let's say, I guess the P naught value is somewhere out here 22 for that particular couple. So here mostly it's in the reduced form, right? When the PE is less than PE naught, right, we expect the reduced form to predominate, and that's what you see here, Cl minus, right, until from minus 10 to a PE value of around 21 or 22, and then let's say when PE is greater than PE naught, right, and that's when obviously you see that the OCl minus concentration, which gradually keeps increasing, is the one that's predominant, and the Cl minus concentration, which is the reduced species, decreases, right. So again, PE less than PE naught, Cl minus or the reduced species predominates, and PE greater than PE naught, you see that it's OCl minus here, OCl minus predominates, right. Again, that's something that we have understood from our particular, what do we say, background and the relevant aspects with respect to redox now, right. So at the same time, obviously we need to look at the relevant, what do we say, so here we had, let's say, Cl minus, right. So something that needs to, what do we say, oxidize, something needs to oxidize it to OCl minus in the real world, right. It's not going to go through by itself, right. Again, because you need a electron, I guess, acceptor, I guess, right. Or here we are having a reduced form, right, yeah, electron acceptor. So again, so we also obviously need to look at the Fe2 plus and Fe3 plus concentration. So let's try to understand where this Fe2 plus concentration is, right. So I believe we have some, this is the Fe2 plus concentration, hopefully, and red one here, which is relatively clear, is the Fe3 plus concentration, right. Again, here we see that Fe3 plus concentration, it's at remarkably low levels, right, but FeOH twice plus concentration, which is the complex, is the predominant form of the Fe3 plus, right. Again, that's something that we are aware of, right, that the complexes are formed, right, especially with respect to the metals, right. And thus you see that the free metal concentration, especially for Fe3 plus, is relatively lower, and you see that the complex that's predominating here is the FeOH twice of +1 charge, I guess, right, and that's what you see here, and hopefully this is the legend for Fe2 plus, right. Yes, this is the one looks like for Fe2 plus. But here let's say if I want to have complete understanding of the system, obviously I can add all the other species that I have not included in this particular graph, let's say, right. I can include all the particular possible species and try to have a detailed analysis now, right. So that will obviously help when I am digging deeper for a particular scenario or such. But let's say if I am trying to look for, let's say, overview of the system, I am about to get something done, I want to know, what the system is, or how the system is going to behave at equilibrium, right, at different conditions now. Let's say in this case, such level of detailed, what do we say, graphics, let's say, are obviously difficult to understand or disseminate, I guess, right. So thus we can look at what are called the predominance area diagrams, which we looked at briefly with respect to our precipitation and dissolution, I guess, right, and even our acid base reactions, right. Predominance area diagrams, as in we are going to identify, let's say, in those regions, let's say if a particular compound is predominant, we are going to identify only that particular compound. So that will give us a snapshot of what we are going to look at. So obviously if you are going to dig deeper and you want to have all the relevant species, Vimintech and log C pH graphs, log C PE graphs, obviously at particular pH or such is going to be remarkably worthwhile. But for snapshots, which it is snapshots or overview or summary of the scenario, right, it would be better to look at the predominance area diagrams. And here we are going to have a look at a particular predominance area diagram, right. And before we go further, I guess I need to highlight that these predominance area diagrams, right. So we have them here for, I believe, the arsenic and oxidation state 5, the two couples, and arsenic in oxidation state 3, right. Arsenic and arsenous, I guess this is not particularly arsenous, H3AsO3 would have been arsenous, and again with respect to Fe3 and Fe2, right. We have the predominance area diagrams for these two couples, right, and here we have Pe on the y axis and pH on the x axis. So in general, I guess in general, obviously the greater the Pe, the greater the oxidizing conditions, the lower the Pe, the greater the reducing conditions, right. And obviously pH more basic, the higher the pH more basic, lower the pH more acidic, I guess, right. Again for this case, I guess for this diagram, I guess I picked one from a publication of my colleague Dr. Sarkar, I guess, right. I wanted to look for one particular example, let's say, that would what do we say, convey or have some practical relevance. So he was looking into some relevant aspects, which obviously we are going to look at. So I guess I am thankful to him. So here we are going to look at predominance area diagrams, and we have the two couples identified, and then we are going to try to understand the system in terms of what we see out there in the nature and why it's relevant, I guess, right. At the same time, we are now hopefully going to bring into play all the relevant aspects we have discussed thus far, right. So these predominance area diagrams, at least the PE-pH diagrams, I guess, right, are also called Pourboy, I guess, right. Hopefully the spelling's right. Yes. So again, you know, a good way to understand the what do we say, summary or get an overview of the scenario, right. But obviously if you are looking at details, you need to look at the relevant what do we say, log C pH graphs, log C PE graphs or such, right. So let's try to understand the system here, right. So here we have on the x axis pH, y axis we have PE, right. So and now here keep in mind that we overlaid two particular PE-pH diagrams. What are they of arsenic 3 and 5, and also for the Fe2 and Fe3 couples, right. So two couples, right. And here let us say the red one obviously corresponds to the Fe3 and Fe2 couples, right, and the blue ones correspond to the arsenic and arsenic forms, I guess, right, the blue ones, right. Say, so let us first try to understand the system, I guess. So when we look at these vertical lines, right, what does that tell us? Vertical lines again, I guess pH, right. If you remember the way we came up with these predominance area diagrams, right, we look at the thresholds, let us say, or those regions when both would be let us say two species would be what do we say, occurring, let us say, or at same concentrations, and try to plot those lines, right, and then to the either side of them we will have either of those species predominant. Yes. So that is how we went about our predominance area diagrams in our acid base or the precipitation and dissolution reactions, right. Again the principle is same. So here the additional what do we say information is that you also have the equation for the PE, right, PE equal to P naught minus 1 by n log of the reduced by oxidized species and so on and so forth, right. So again in the same way you can get that done, I guess, right. So again that is not what we are up to here, we are only going to try to understand the system now, right. So when in general let us say the solid line means there is only a change with solid vertical line, or vertical line means again it is with respect to just the pH, so only a change with respect to H plus, I guess, right. So similarly let us say a horizontal line, let us say do we have any horizontal lines here, okay, there is one right here, means change with respect to electrons, but no H plus are involved here in that particular transformation, as in with respect to the equilibrium between Fe3 plus and Fe2 plus, right. We know that it is just, the equation is just Fe3 plus electrons goes to Fe2 plus, right. So obviously no H plus involved here, so that is why you see a horizontal what do we say line here, right. And obviously here again I guess it is between Fe3 plus and FeOH thrice, right. It is just again H plus involved here, no electrons. So that is why the vertical line in general would correspond to, let us say, just the involvement of H plus and no electrons, I guess, right. So in such case, I guess you can understand the relevant aspects involved, right? So first let's try to understand the system with respect to the pH, I guess. So obviously at acidic conditions, you know that Fe3 plus or the free metal will be predominant, but it should be at remarkably, what do we say, acidic conditions. And in most of the at a greater range of the pH, as you can see here from, as I move from what do we say, pH 0 to 14. So from pH 3 to 14, it's the, what do we say, solid, right, say, right, FeOH thrice, that's predominant, right, and not the free metal anymore, and maybe a few complexes too, I guess, right. And again, if we look at it with respect to arsenic here, let's say, and what do we see here? Here it's H3AsO4, and in this zone between here and here, right, you see it's H2AsO4 minus, and here and here, and between the pH of 7 and approximately 12, right, it has HAsO4 2 minus, and from around 12 or 11.8 to 14, it has AsO4 3 minus, right. So again, this is nothing but the speciation with respect to the dissociation of, or due to dissociation of the proton, I guess, right. So H3AsO4, so if the pKa was around, I guess I'm assuming it's around 2.2 or something like that, right. So it obviously deprotonates, and when the pH is greater than pKa, right, which is the pKa line corresponding to this obviously, and in this region you end up having the deprotonated form H2AsO4. So the pKa2, I guess, is around 7, right, around 7, and thus when the pH is greater than pKa2, you again see the other deprotonated form HAsO4 2 minus. When pH is greater than pKa3, right, you see that the most deprotonated form predominates, right. So let me just look at another figure here. Yes, so here again we have some background with respect to our acid base relevant chemical process, and here we have some with respect to Fe3, we have some background related to our complexes, right, complexes which are obviously pH dependent, and precipitation and dissolution, right. So now let's try to understand the system with respect to the vertical axis or the y axis. So let's say, let's look at it here, let's say, right. So obviously Fe3 plus, right, when Pe is, what do we say, greater than Pe naught, and I guess looks like Pe naught is somewhere out here. When Pe is greater than Pe naught, we know that the oxidized species typically predominate, right. So in this region you see that the oxidized species or Fe3 plus predominate, and in this region, right, you see that the reduced form or the Fe2 plus predominates, right. So that is what you see out here. But obviously as you shift, right, the pH, it is not the equilibrium between Fe3 plus or Fe2 plus, but the equilibrium between FeOH thrice and Fe2 plus, I guess, right. So that is what you see here as you shift the pH here, yes. But for a broader what do we say, range of Pe and pH values, you see that the equilibrium is between FeOH thrice and Fe2 plus, but only at very low pH, right, right, and high Pe values would you have any Fe3 plus, right. And again same case here, but with respect to arsenic, let us understand the system though, right. Here we have, let us say, a particular, what do we say, threshold, I guess, right. So obviously a sloped line, what does that mean now, right? It means that the equation has both the electrons and H plus, electron transfer and H plus involved in the particular reaction, right, unlike just the vertical or the horizontal lines. So here now let us say this is the line that gives us the boundary between, let us say, the arsenic 3 and arsenic 5 forms, right. So again the boundary between arsenic 3, so here in this region we have what do we say, arsenic in 3 plus oxidation state predominant, and above it obviously arsenic in 5 plus oxidation state predominant. But obviously again as you vary the pH, you see that H3AsO4, H2AsO4 and so on, right. So with respect to one particular example, I guess we did look at this particular aspect, as in if you want to remove arsenic by, let us say, ion exchange process, let us say, right. So which form would you want to predominate? As you see here, in most of the pH, right, if it is the reduced form as in AS3, HASO2 would be neutral, right, it has no charge, right. So will that be suitable for removal by ion exchange? No. But let us say if I consider the more oxidized form, let us say arsenic in oxidation state 5, I see that even at pH, let us say from 2.2 or something like that, it has a charge, and at neutral pH it is either in HASO4 minus or HASO4 2 minus, right. So, it has a charge on the the compound has charge on it. So, obviously if it's charged at the neutral pH, it is relatively obviously amenable to be removed by the ion exchange process, and I think this is one example that we have looked at, but this gives us an understanding of it. So, again we have taken considerable time in understanding the relevant aspects. So, now let us try to see the practical relevance, I guess. So, here we have, let us say, a region that is supposed to conform to the groundwater now. So, I guess here the pH is we are saying is going to be between 6 and 8, let us say, right, and the Pe values for groundwater typically, I guess, right. Okay. So, in this region let us try to understand which forms of either arsenic or the iron are going to predominate now. Here as you see, let us say here, let us say in this region, right, which form predominates now? Arsenic, let us say in oxidation state 5, mostly as HASO4 2 minus, and iron, which form predominates? It is FeOH thrice this solid, right. So, what does this, or how does this affect the system now? So, as you know, let us say as solid is formed, let us say, or the Fe3 plus precipitates at this particular range of Pe and pH, right. It also allows for co-precipitation of this arsenic 5, right, makes sense hopefully. If the Pe pH range is within this particular area, let us say, we know that ferric iron, right, is going to precipitate, right. And similar to what we have looked at with respect to our coagulation and flocculation, one of the aspects we looked at was co-precipitation, right, as in you have these particular FeOH thrice solid particles upon which you can have adsorption and thus co-precipitation of various other compounds here. And so, thus let us say whenever you have this in this particular region, I guess the arsenic will be removed by co-precipitation on this ferric hydroxide precipitate, yes. But obviously if it is in this particular range though, right, what is going to happen? We see that it is in arsenic 3 form, and also that its iron is in Fe2 plus form. So, it is relatively more mobile, right. I mean, as in here it has no charge, arsenic has no charge, and Fe2 plus, as we know, mostly stays as Fe2 plus, right. So, here let us say if this particular groundwater conditions fall within this zone of Pe and pH, right, we see that arsenic 3 form is going to predominate, and also Fe2 plus, and arsenic 3 is going to stay in solution. Unlike the other case when we had, let us say, FeOH thrice and arsenic 5, we saw that co-precipitation is going to occur. So, the arsenic concentration in the water, right, is going to be less or negligible, obviously depending upon the amount of precipitate that is available or being formed there, right. So, again that is particular understanding with respect to estimating, let us say, the concentrations of arsenic, carcinogen, toxic compound and such, right, in your particular system now. So, now let us say one other aspect is, let us say, in your leachate from your mines, let us say, right, and here looks like the relevant Pe pH range is within this particular area now, right. So, what do you see here now in this particular Pe pH range, which corresponds to leachate, let us say, yes, from your mines, you see that arsenic stays as As3, right, in its oxidation form of the 3 plus. It can also stay as H3SO3 too, right, not just HASO2, but both the oxidation states of arsenic are still 3 plus. So, but here though you see that it is Fe2 plus and arsenic in its 3 form. So, what does this mean now? Arsenic, again, as we have seen in our case with respect to our groundwater, arsenic concentration is going to be present in, if any arsenic is present, arsenic is going to be present in the groundwater or the water itself, right. It is going to be dissolved, and thus it can transport over a greater distance, let us say, or the plume can travel greater distances, right, depending again on the P and pH conditions, leading to contamination of a wider area, yes. So, that is one particular aspect. But let us say if your particular leachate, let us say, or such has been in equilibrium with the atmosphere, as in with respect to oxygen, let us say. So, then obviously your Pe values will be relatively higher. So, that is why let us say for the spent sludge, let us say the pH range is somewhere out here now, right. So again, for the spent sludge, we are trying to understand it, what form or what are the issues, let's say if arsenic is present in water and pH ranges, and then if it's in leachate, which we usually see in our acid mine drainage, let's say, and such, and if it's in spent sludge, let's say, which is in equilibrium with our atmosphere, what would be the case, let's say. So if it's spent sludge, it's going to be in equilibrium with your atmosphere or with oxygen. So obviously more oxidizing conditions prevail, that's why you see that the pH range is somewhere out here. And obviously what do we see here now? At this particular range of P and pH, we see that arsenic 5 predominates, and at the same time you have ferric hydroxide precipitating. So again, you are going to have co-precipitation of arsenic on this ferric hydroxide, right, and thus removal of arsenic from your sludge here, or at least from the water here, right. So thus if I just filter out the relevant if I just use the right filtration techniques, I can remove this ferric hydroxide and the relevant co-precipitate of arsenic on this particular ferric hydroxide, and thus have relatively treated water. Yes. So again, this hopefully gives you an understanding about which species predominate at which particular P or pH and why they are relevant, right. So here that's one particular case where this example is relatively worthwhile, as in if it's in groundwater, which species would predominate, and if it's in the oxidized form, let's say, or oxidizing conditions prevail, we saw that arsenic can be removed from groundwater because it can precipitate out along with FeOH thrice, right. So again, hopefully this particular example gave us or gave you, let's say, a snapshot or overview of all the process involved, as in we have looked at complexation, we have looked at, let's say, acid base chemical process here, and the redox process and so on, and more importantly tied that up to what it is that we expect out there in the nature, right. So again, I guess with that I am going to end my chemical process related course. Again, so this hopefully was intellectually challenging for most of you guys out there, and hopefully you enjoyed the homeworks too, I guess. And thank you for your time. And again, I guess I thank my advisor, Dr. Bill Batchelor, from whom I have learned all these relevant aspects, right. And again, thank you all for taking this course.